Hello everyone, and we are now on our last section of forces, of the Coulomb's force or electric forces in Physics 112 or Physics 131. So if you haven't done the reading, please get to it. It's Untitled Chapter 17 if you have that book. If you're in college physics and you have open SACs, it'll be Chapter 18. And if you're doing Physics 131, it'll be Chapter 7 in Volume 2. So please get started on your homework. What we're going to do today is we're going to now integrate what we learned in Physics 121 and all the different forces that we learned in Physics 121 and how you're going to then integrate them in with this Coulomb Force stuff. So let's do something real quick. Let's talk about all the different types of forces that we learned. Well, in Physics 121, I'm going to mark up this document by hitting comments, and then I'm going to close it, and that will give me these tools up here that I can then mark this up. So one of the non-contact forces that we learned about was the force due to gravity, and that's the force of the Earth pulling on you, and that was equal to the weight of the object. Okay, and that's just mass times gravity. We had learned about the Coulomb force, by the way, is just F sub Q, and that's going to be K Q1 Q2 over the distance apart squared, and absolute value of that. So those are the two non-contact forces that we are now dealing with. Okay, everything else is a contact force. That means the object has to be physically touching you. So some of that is just a force of a push or a pull. Right? Just like a hand or something. We'd also learned about the normal force, right? If you have a block on a surface, that surface is going to cause a force directly perpendicular to its surface, and thus that's why they call it the normal force. So it's a normal force, right? And it's just a surface force. And that could be caused by a wall, a ceiling, or any surface, a desk, anything that you want to call it. There's the rope force, which is a tension, right? So anytime you attach a rope to something, that is a rope or a string, that is going to be called the tension force, all right? And then finally there was a friction force, okay? And it was a weird friction, so we're going to call this friction. And that was equal to this weird F, and that was either equal to mu sub K or mu sub S times the normal force. Remember that? And that static friction is when the object wasn't moving. Static friction, mu sub S, goes when an object is not moving, and mu sub K is when there is a velocity vector. Mu sub S goes with an object that is not moving, while mu sub K is associated with an object that does have a velocity vector. Okay, and there are two different situations. Most of our problems, the objects are sliding or something like that, so it'll be mu sub K. But don't forget, it's times the normal force, which in this case would probably just be mass times gravity. But it's not always mass times gravity. If you ever have a normal force on a surface like this, mg is going to be pointed down and to the right. The normal force is going to be pointed up. And so that normal force is actually going to be, this will be theta, will be equal to mg cosine of theta pointed down. Okay? So you have to remember that normal force is not always equal to mg. If the object is accelerating up or down, or if the object is on an inclined plane, then that normal force is not going to be mg. Okay? So that's just a quick review. The one non-contact force we learned in Physics 121 was mg. Now we're adding a second one called the Coulomb force. That's going to be K Q1 Q2 over r squared. But then all these other guys are contact forces. So that means they have to physically be touching the object. And that could be a force of push or pull, a normal force, that's a surface, a rope, or friction, right? So those are the 4 different kind of contact forces that we learned about. So here is a really great problem. So what we have is we have a glass bead, a small glass bead. It's charged with negative 10 nanocoulombs. A nanocoulomb, by the way, is 10 to the negative 9th coulombs. Okay, so you have a plastic bead with 10 nanocoulombs, or 10 times 10, negative 10 times 10 to the negative 9th coulombs. And this bead is held 1 centimeter above another glass bead that rests on the table. The bead has a mass of 15 milligrams. Okay, so that is going to be 0.015 kilograms. Okay, and it's going to leap up off the table. Okay, and they're basically asking the question, will the object leap up off the table? So let's draw this out. So our model, what we're going to do is we're going to go ahead and draw this out. So we have a positive 10 nanocoulomb object sitting here on the table, and it's got a mass of 0.015 kilograms. And up here is an object stuck in place, and it is a negative 10 it's a negative 10 nanocoulomb object. Okay, and these guys are a distance of 1 centimeter, which is 0.01 meters apart. Uh, 0.01 meters apart. Okay, well, they're asking, will it accelerate up towards this? All right, well, let's do our force diagram. So we're going to be doing a force diagram on the positive 10 nanocoulomb object. And that is because we are asking the question, will the positive 10 nanocoulomb object move upwards? So let's set our coordinate system around this. And I don't think we need to draw the x-axis, but we're going to do it anyways. And let's go ahead and think about what forces are working on this. Okay, well, the positive 10 nanocoulomb object is sitting on the table, okay, and they're asking, will it leap into the air? Let's think about which one of these forces over here are acting on it. Okay, so since there are charges involved, and obviously we're in the electric force part of the chapter, there's going to be a Coulomb force acting on it, and this object does have a mass, so it's going to have an F sub q and also an F sub g working on it. But is there anything touching it? Is there a hand touching it? Is there a normal force? Is there tension? Is there friction? Let's think about it. Well, this object, they did say it is sitting on the table, right? So that means this positive 10 nanocoulomb object is sitting on a flat surface, okay? So let's go ahead and draw force diagrams. Well, this positive 10 nanocoulomb object is going to be attracted towards that negative 10 nanocoulomb object. So it's going to have an upward pointed force, right? It's also going to have a downward pointed non-contact force that is the mass times gravity of this object. Okay. Also, since it's sitting on the table, so those are the two non-contact forces. Now everything else acting on the negative 10, with the positive 10 nanocoulomb object has to be a contact force. So this positive 10 nanocoulomb object is also sitting on the ground, which means it's going to have an upward normal force working on it, pointed in the positive y direction. Okay. Now, it's not moving, nor is it accelerating. Well, we don't know the direction of its acceleration, and I think that's what they're asking. We don't know if it's moving. So we're going to find out both of those, but I think they want to know if it actually does accelerate upwards. So they're asking, is the acceleration up? Okay, well, let's do our force diagram. Okay, I'm going to switch to black ink. And since we don't have any forces acting on it in the x direction, we're only going to need to sum the forces in the y direction. So we're going to apply Newton's second law in the y direction. Okay, and I'm going to write what I'm seeing. I see a negative mg pointed down. I see a positive normal force pointed up. And I also see a positive Coulomb force pointed up due to the negative 10 nanocoulomb charge up here. And we're going to be asking the question, does this object accelerate upwards? So this is what we're solving for right here. This is what we need to solve for, is that acceleration. Okay? Okay. Let's think about this for a second now. Well, let's think about this in a weird, different way. Like, if this force right here is greater than this force, so if the Coulomb force is much greater than the mass times gravity force, okay, much greater than the mass times gravity force, then the object should be accelerating upwards, right? But if the mass times gravity force is greater than all of the other forces, then much greater than the Coulomb force, so let's say mg force is much greater than the Coulomb force, then there will be a normal force, and that means that it won't be accelerating upwards. So this is kind of the situation that I'm actually thinking. Rather than focusing on acceleration, I shouldn't have actually, I should have focused on the normal force. Okay, so let's do this. Let's compare the Coulomb force to the mass times gravity force. And I'm going to bring the normal force onto the other side. Okay, so basically, if this force works out to be positive, okay, if this force right here, if the sum of these two forces right here works out to be negative, then there will be a normal force and no acceleration. So basically, if this works out to be negative, then there is a normal force, and acceleration is 0. If it works out to be positive, then there will be an acceleration, but no normal force. Okay, so let's just concentrate on these two here. So negative mg is going to be, so the mass is going to be 0.015 kilograms, and that's times 9.8 meters per second squared, plus that Coulomb force is going to be K, and that's going to be times 10. So we're doing our force diagram on the positive 10 nanocoulomb object minus 10 nanocoulomb object all over their distance apart, which is going to be 0.01 meters that you're going to square that whole thing. And again, hopefully this works out to be a positive, and if it does, then that means the normal force is 0 and it will be accelerating upwards. Okay, so let's find out what this number is right here. I'm going to do this. That is going to be 9.8 times 0.015. All right, and that is going to be negative 0.147 kilogram meters per second squared. This part is going to be 10 times 10, so this is going to be 9 times 10 to the 9th, okay, and that's going to be times 10 nanocoulombs, which is 10 times 10 to the negative 9th. So these two are going to cancel out. So this is just going to be 90, and this is times 10 to the 10 to the negative 9th, and that's going to be all over 0.01, which is going to be a really small number, 0.01 times 0.01, and that's going to be 1, 2, 3, 4, so it'll be 1 times 10 to the negative 4th when we multiply that out, meters squared, okay, and this is going to work out to be 90, it'll be actually 9 times 10 times 10, so this is going to end up becoming 900 times 10 to the negative 9th, all over 1 times 10 to the negative 4th. So that is going to be, that'll be 900 times 10 to the negative 5th. So 900 times 10 to the negative 5th is much smaller than this, than the weight, which means the upward force is going to be smaller than the downward force, which means there is going to be no acceleration and there will be a normal force. So that means this whole thing, there will just be a normal force, and mass times acceleration in the y direction is 0. All right. Well, let's check our work. Well, here they draw their force diagram, okay, and they've labeled their Q's just like we have, and they've labeled their force diagram. And they've kind of given us a clue that the force due to the Earth, or mass times gravity, we call, in my force diagram, we just call that mass times gravity. They've given us a clue that this is a large arrow down. So basically, here's what they're saying, is that the Coulomb force, which we calculated, is going to be 9 times 10 to the negative 3rd, or what we calculated as 900 times 10 to the negative 5th. This is actually the same thing as 900 times 10 to the negative 5th newtons. And that is in comparison to 1.5 times 10 to the negative 4th. So basically, oh, actually, you know what? I forgot that this was, why is this so, I think I made a mistake here. Hold on a second. This, let's try this again. 0.015 times 9.8. Oh, that is, I forgot a 0. That is 0.0015 times 9.8. Oh boy. 1, 2, 3, 4. Yeah, so this is actually much smaller than I thought. 15 milligrams. 1, 2, 3. Yeah, so really this force, sorry about estimating that wrong. This is actually going to be a much smaller force than this one. So actually the object will have no normal force, and it's going to be accelerating upwards. So hopefully you learned a little bit from my mistakes, but this is kind of the approach that you do when you're integrating your knowledge from 121 to 131. You have to now consider another force. It's two non-contact forces, right? You've got mg, and you have this kq1, q2 over r squared. But then you have your contact forces, right? You've got your just basic force of a push or a pull. You've got the normal force. You've also got a rope or a tension force, and you also have the friction force. So there's those 4 non-contact forces that you have to consider as well. And so you're going to have a couple problems in your homework and in your lecture tutorials on those that we could probably do when we're doing our WebExes. Okay, so I hope you had a good time, and I'll go ahead and we'll go ahead and begin working on your sapling homework, and then we're going to move on in the next section. We're going to move on to electric fields. So this is going to be how charges create electric fields. All right, have a nice day.